Good afternoon, students. In the week 3 of Advanced Robotics course, we have covered about forward kinematics and inverse kinematics. So in this session, I will talk a bit about both these concepts and will solve some questions regarding these concepts. So firstly, why do we need inverse kinematics and forward kinematics while working with robots? So let's start with the very basic example. Let's say there is a manipulator which I am drawing with end effector position given as x comma y, and it's a 3 degree of freedom 3R manipulator, right? So any such manipulator in reality has these joints with some actuation to move these joints, and generally for revolute joints we have a gear train, a motor, and an encoder, right? So I will draw this separately here. At the joints we have the gear train, the motor, the encoder. Right. So the motor provides the torque, the gear train multiplies the torque, and the encoder, or the joint encoder as it is commonly called, is a sensor to measure position and velocity of the motor. So basically, using the encoders, we can get the data about the joint angles. Similarly, in prismatic joints, we will have some other type of sensors which will tell us what is the distance which the joint has moved. So now any task that a manipulator does, it has to move from let's say point A to point B. This could be some task that follow a trajectory from point A to point B. Another task could be just to hold its position at a certain given desired position and orientation of the end effector. So the task could be hold a EE pose. E is end effector and pose is position plus orientation, right? And the second could be, so first one is a static task, we have to just stay at that position, and the second could be follow a trajectory, right? Now in either of these tasks, what we have to command, we have to command the joint angles, right? Now that joint angles can be directly given to the motor or given in form of torque commands, but in the pipeline of making that manipulator move or hold a position, what we need to know is the joint angles. What are the angles that each of these joints should be at in order to have the desired pose of the end effector, right? So This requirement comes out naturally from the task that we have in mind, that we have to do using these manipulators, right? And naturally, the requirement can be formulated as, given a pose of end effector, what are the joint angles, right? This is the first question. And the reverse of this question would be, which would also like to know in certain cases, that given joint angles, what is the pose of end effector, right? So these are the questions which are answered respectively by, the first one by inverse kinematics, and the second one by forward kinematics. So moving ahead, we can draw a flow diagram like this. Inverse kinematics, or it is commonly written as IK, takes the joint angles. I will denote the joint angles as, the vector of joint angles as Q, no, let me correct this. So I should draw, yeah, so IK takes the end effector position, let me draw it as the X vector, and gives the joint angles. And forward kinematics block does the reverse. It takes in the joint angles and gives us the pose of the end effector, right? So, and as we have established, these two operations are very crucial in any robotics applications. So it's very necessary that we understand these operations in depth, and also understand the mathematics behind them, and different manipulations that we have to do while doing inverse kinematics and forward kinematics for different systems. So now let's introduce some terminologies which you should be familiar with. First is configuration space, also can be said as the joint space, and the second is the task space. So what are these two terms which are required to proceed to our further discussion on kinematics? So let's take a 2R manipulator, the simplest manipulator example, and let the angles be Q1 and Q2. This is the end effector whose position is given as x, y. So the joint angle vector is Q1, Q2, and the end effector position, since it's a 2D plane and we are not concerned about the orientation of the end effector, it's fully specified by its location x, y. So the configuration of the manipulator is fully specified by these two coordinates, and the space spanned by these two joint coordinates is called the configuration space, or the C space, right? So any physical device has some limits, right? So let's say we have put some limits that q1 can vary from minus 45 degree to plus 45 degree, and q2 can go from, let's say, minus 80 degree to plus 80 degree, right? So this space, if we make a plot between q1 and q2, right? So, and since we are taking negative values also, let me extend it this side. So q1 can take values from here to here, let's say, and q2 can take values from some limit to some limit. So this region, this shaded region, is the all the possible combinations of q1 and q2 lie in there. So that's the C space of this system, right? And task space, as the name suggests, is the space in which we specify the tasks, and usually it is also called the Cartesian space, since that's the coordinate system that we use most of the times to specify the tasks. So why task space? Because we can specify that make this uh, make this manipulator go to, let's say, point 1 comma 2, or move this manipulator from 1 comma 2 to 5 comma 10 while following a trajectory. At each point we can know, we have the information about the x and y coordinates, right? So precisely what we specify for the manipulator is the coordinates of the end effector, right? And that's the task. So the task space is the set of coordinates which are used to specify the task, right? And the relation between task space and C space is not linear, mostly. Even in the case of the simplest 2R manipulator, it's not linear, which means that let's say I'm starting from some configuration of joints, let's say q1 0, q2 0, and I follow a linear path to q1 1 and q2 1, right? Then this does not imply that in the task space it goes from x1 y1 to some linearly to x2 y2. Generally it traverses a non-linear path, right? So this is a point that has to be kept in mind, that the movement from configuration space to joint space, that is not linear, and as we will see, we will find the mathematical expressions that will show why this transformation is not linear, right? So now that we have established why we need inverse kinematics and some basic terminologies, let's go on to the techniques that are there for inverse kinematics. I will be covering most of the uh, time about inverse kinematics, because that's the thing which is, I would say, more involved, right? Has more layers into it rather than forward kinematics. So spending time of on inverse kinematics is more crucial. So inverse kinematics for any system can be either be solved analytically or in a closed form manner, or the second could be iterative or numerical approach, right? So the advantages of the advantages of analytical approach is that uh, it gives all the solutions, all the possible solutions for a given pose of the end effector. Also, it can be tedious to derive at first time, but once computed, it is very fast to evaluate, right? Because you have closed form expressions which you just need to evaluate, right? And also, you need not guess anything, right? No initial guess is needed, right? And the cons can be that it has to change for once the system changes, because they are closed from expressions, so you have to rederive the new expressions for the new systems, right? So rederive, and that can be tedious as the systems get more complicated, right? And also analytical methods generally do not perform well with uh, redundant systems. I mean, you have to be more careful there since there is a multiplicity of solutions. So what's the inverse kinematics problem? Let's state it mathematically, right? So basically, we have to there is a there is a function, right, which takes in joint angles and gives the pose of the end effector. This is forward kinematics. In the inverse kinematics, we have to find the inverse of that mapping from the end effector pose to the joint angles, right? So we'll first see analytical approach. The iterative approach I will just briefly touch upon later, but first we will see analytical approach, and that also for the simplest example of a 2-hour manipulator. So I will derive the inverse kinematics equations for a 2-hour manipulator, right? So any given manipulator, if it has n degrees of freedom and let's say there are m task constraints. The constraints, let's say for the 2-hour case, that the x position should be some given position of end effector, the y should be some given position of the end effector. So that is a task constraint. So these two numbers can be compared, and depending on that, we can say, just by looking at these two physical quantities, what are the possible number of solutions, right? So n is less than m, that is the degrees of freedom of the manipulator is less than the task constraints. So in this case, there is no solution. Let's say I have a 2-hour planar manipulator and I specify that x should be x0, y should be y0, and the z should be z0, then there is no way possible that it can reach that z coordinate because it has no degree of freedom to move in that direction. So there is no solution in that case. The second case is when the degrees of freedom is equal to the task constraints. That is the case that we usually see, is that there are specified coordinates x and y for the end effector, and there are two joint angles that are 2 degrees of freedom. So in this case, there is a finite number of solutions. Note that I'm saying finite number of solutions, not one solution, right? Because as you will see very soon, that there can be multiple solutions, but the solutions will be finite. Now, third case is when the number of degrees of freedom is more than the task constraints, right? So this is what when we say that the manipulator is redundant, or there is a redundancy in the manipulator. So in that case, there is a possibility of either infinite solutions or no solutions also, right? Infinite solutions could be that a 3R manipulator, right, which is, let's say, planar only, and we specify, right, so a 3R manipulator in plane, a 3R manipulator in plane is redundant, because to move in the xy plane we only need 2 degrees of freedom, and this has 3 degrees of freedom, right? So this is a redundant manipulator, and to reach any desired position, any desired pose of the end effector, it can have multiple configurations. Let's say I will draw some more here. So another configuration could be this, right? Another can be, let's say, like this, or so. When you solve mathematically, you will find that because you will be solving some set of equations, and the constraints are less and the number of variables are more, so there will always be infinite solutions to this kind of a mathematical system, right? So that is about the number of solutions for a IK problem, and just by looking at the degrees of freedom and the task constraints, you can tell how many solutions can you expect for that IK problem, right? Now let's proceed to the, let me make some space first. Okay, we have enough space now, so let's continue. So what we will see is 2R manipulator and its analytical IK, right? So let me first draw diagram afresh and give very clear notation. I would suggest everyone to do this on your own, because this is one of the simplest manipulators and one of the most common classroom problems that you would solve, right? Wait, let me draw it like this. Okay, this is the end effector. This is the first joint O, this is the second joint A, and this is the end effector B. So let the position of the end effector be given by Px, Py. Let the lengths, so what is the physical quantities involved here which are fixed, that is L1 and L2, right? And the joint angles are theta 1 and theta 2. Okay, so in the previous week's assignment solutions or discussion hour, we have seen that how to express px in terms of the link lengths and the joint angles. So let me just directly write px is L1 C1, and the notation I will rewrite once again. So C1 is cos theta 1, S1 is sin theta 1, C12 is cos theta 1 plus theta 2, and similarly sin 12 is S12 is sin theta 1 theta 2. Okay, so px is L1 C1 plus L2 C12. Py is similarly the y coordinate L1 S1 plus L2 S12. So we name it as equation 1 and as equation 2. So the known quantities are the end effector position, since we are doing inverse kinematics, the link lengths, these are known quantities, and the unknowns are the joint angles theta 1 and theta 2. So the goal is to find theta 1 and theta 2 from these two equations, and what will follow is a series of manipulations, mathematical manipulations we'll have to do in order to find closed form solutions for expressions of theta 1 and theta 2. Right, so let's begin the first part is, first we'll finding theta 2. Okay, so for finding theta 2, what we'll do is square the two equations and add them. So px square plus py square. So the expressions of the two positions I will rewrite once again. Square this plus L1 S1 plus L2 S12 square again. Now let's open these squares. So L1 C1 square plus L2 square C12 square plus 2 L1 L2 C1 C12. Similarly for this, L1 square S1 square plus L2 square S12 square plus 2 L1 L2 S1 S12 equal to, now remember that cos theta 1 square plus sin theta 1 square is 1, so this term and this term equate to L1 square, this term and this term equate to L2 square, and what we have remaining is 2 L1 L2 common, and we have C1 C12 plus S1 S12. Right, now this expression is, I'll write as a little bit expand form, cos theta 1 theta 2 plus sin theta 1 plus theta 2. this is the, if you will see, if theta 1 is A, theta 1 theta 2 is B, then this is cos A cos B plus sin A sin B, and this is the trigonometric expansion for cos B minus A, right? Or A minus B, since cos theta is equal to cos minus theta, we can choose either. So in our case, B is theta 1 plus theta 2, A is theta 1, so B minus A is theta 2. So the further simplified expression is L1 square plus L2 square plus 2 L1 L2 cos theta 2. Now on this side, what we had is px square plus py square, which are known quantities, and on the right hand side we have L1 L2 and C2. So we only have one unknown in this equation, cos theta 2. So the expression for cos theta 2 is L1 square plus L2 square. Wait, first we'll have to write px square plus py square. So px square plus py square minus L1 square plus L2 square by 2 L1 L2. Alright, so theta 2 will be so we can directly write theta 2 from here also, but this might not give us the solution that we require, right, for theta 2. So a good practice is to find sin theta 2 also, and then so a good practice is to find sin theta 2, and that will be plus minus under root 1 minus c2 square, right? And here you see two solutions, which I will come to later. And finally theta 2 is calculated as arctan 2, which is a commonly used tan inverse operator in programming, so borrowing from there, and it takes the two arguments. First is the what is called as y and then x. So if tan of theta 2 is y by x, so tan inverse of y by x is theta 2, and the using a tan 2 is that its range is minus pi to pi, which is commonly used in robotics application. So in robotics, wherever you will need to take tan inverse, you have to use a tan 2. Now we have the expression, a closed form expression for knowing theta 2, and at this stage let's evaluate the expression for theta 2, right? So if now cos theta has to be between minus 1 and 1, we all know, right? So if the RHS is greater than 1 or RHS is less than minus 1, then we have no solution for theta 2. And what are those cases? So RHS will be greater than 1 if so If the right hand side is greater than 1 or less than minus 1, then we would have issues in finding a solution. We would not find a solution, right? So in this case, when it's possible that the thing at the top is greater than 1, right? When so if px square plus py square is greater than, let's say, the total length of the manipulator. So the total length of manipulator is, what's the maximum distance it can reach, right? So the distance of the point from the origin, the end effector point that we want to achieve, is root of px square plus py square, and the total length of the manipulator is L1 plus L2, right? So if px square plus py square is greater than, squaring both sides, we get L1 plus L2 whole square, right? Now if we further expand this, we will have px square plus py square is greater than L1 square plus L2 square plus 2L1 L2, right? And if we rearrange the terms to get a familiar expression as above, we will get that if this is this quantity is 2L1 L2 is greater than 1. So the conclusion is, if px square plus py square is greater than L1 plus L2 whole square, then the RHS is greater than 1, right? And that is expected also, that end effector of the manipulator cannot be at a point whose distance from the origin is greater than the maximum length of the manipulator, right? So the manipulator can reach in the plane a maximum length of n1 plus L2, right? And if the desired point is outside it, it cannot reach there. So we will not find any solution for the joint angles which will give us the desired end effector position, right? And the second case would be, and that is for when the end effectors are of different length, that is, the second end effector is shorter than the first end effector, so there is a space inside it which it cannot reach. So basically there is an annulus. As you would remember in the previous discussion hour, we drew the workspace of a 2R manipulator when the link lengths are not equal, right? So there is an annulus, and this is the case when the second link is shorter than the first link, right? So in that case, if the point lies inside this, right, then also there will be no solution. So if those cases are satisfied by the end effector position, then at this stage only you would declare that there exists no solution to this inverse kinematics problem, right? Now getting back to our primary derivation, which is to derive the expression for the closed form expressions for the ik of 2R manipulator. So we have the expression for theta 2, right? So let's continue with the second part, which is finding theta 1, right? And this involves more mathematical manipulation than theta 2, so please follow carefully here. Let me rewrite the two equations of px and py. So first, now there are multiple steps involved here. So first step, what we do is we multiply the first by c1 and multiplied the second equation by s1, that is sine theta 1, and what we will get is L1 C1 square plus L2 C12 C1 plus L1 S1 square plus L2 S12 S1, right? And again L1 C1 square plus L2 S1 square is L1, and L2 is common in the two terms, and that's the same expression which we encountered earlier, cos A cos B plus sin A sin B. So this is L2 C2. The second equation, manipulated equation, which we will get is by multiplying the first equation by S1 and the second by C1. Okay, so what we get here is minus L1 S1 C1 minus L2 S1 C12 plus L1 S1 C1 plus L2 S12 C1, right? So here first these two terms cancel out, and what we have in hand, L2 is common, and what's inside is S12 C1 minus S1 C12. Now this expression is another trigonometric expansion that you will use, that is sin A cos B minus sin B cos A is sin A minus B, right? So we will get L2 S2. Okay, so we make some space here. Okay, this works a little bit weirdly. So let's continue here. Note that this is a derivation continued. Continued derivation. Okay. So the two new equations which we have are we have px c1 plus py s1 is equal to L1 plus L2 C2 and minus px S1 plus C1 Py is equal to L2 S2, right? Now what we'll do next is multiply the first equation by Px and the second by Py. Okay, so the first equation which we will get is Px square C1 plus Px Py S1 is equal to L1 Px plus L2 C2 Px. And the second equation is Px Py S1 plus C1 Py square is equal to L2 S2 Py. Okay, now we add these two equations. So what we do, we add them. So on the left hand side we have Px square plus Py square, and both have the common term cos theta 1, and these two terms get cancelled. On the right hand side we have Px L1 plus Px L2 C2 plus Py L2 S2, right? So C1 is Px L1 plus L2 C2 plus Py L2 S2 divided by Px square plus Py square, right? So now whatever terms are there on the RHS, we know them, right? We know the cos theta 2 value, and we know all the quantities L1, L2, Px, Py. So this is the term for cos theta 1. As we did for theta 2, we will find sin theta 1 using the trigonometric relation, and theta 1 will be A tan 2 S1 C1, right? So this is the end of proof, or the derivation, right? Not a proof. Things to note is that I talked about multiple solutions a while ago, and let me show you. So we saw mathematically that how the multiple solutions arise, and physically also, if you want to have an intuition, you can have it. So this can be one approach or one way to reach this point, while the other can be, or let me draw it with a different color. Right, and like this. So the end effector positions are the same, but the joint angles are different, right? So in this case, so you remember the theta 2, we had plus and minus sign. So these are the two theta 2's, and this is the first theta 1, this is the second theta 1, right? So this is commonly in the 2R manipulator terminology, this is commonly known as elbow up, and elbow down. So borrowing from human analogy, if this is the elbow, right, so this is elbow up and this is elbow down. Okay, so what else do we have? So now that we saw how to get the inverse kinematic x of 2R millimeter expression, so let's first go through the questions of uh, week 3, right? And then if the time remains, we will discuss a few other things. So the first question is, a Puma robot is shown below. The frames have been assigned the second row of DH table, right? So the DH table for this robot has been derived in class in full detail, and I refer you again to those lecture slides, and you can easily see there that the second row of the table is this. So not much inside here, just straightforward. Once you assign the frames correctly, right, then it's a straightforward task. The important thing to note here is that, and there's a question also on it here, that the last 3 axes intersect, right? So here these, the Z4, the Z3, right, they are intersecting. Okay, next question is, forward kinematics is defined as given the joint angles and link parameters, find the, what do we have to find? As we discussed, the position and orientation of the last frame, or the end effector E, right? So Fk is given the joint angles, these are the joint angles, and this is the end effector position, which usually is attached to the last frame. Okay, in the 6 degree of freedom Puma robot, the last 3 axes are orthogonal and intersect at a point, right? So as I mentioned just a while ago. For the 2 degree of freedom 2R planar manipulator, shown below, the coordinate xy is given by, so again this is something which we have now seen repeatedly, and you would now recall the constructions needed, right? So this is L1 C1, this is L2 C2, marked as P1 P2 P3 P4 and P5, and let's say P6. So P1 P2 is L1 C1, P2 P3 is L2 C12, yeah, this is C12, because this entire angle is, that's the only thing to note here, that the entire angle is theta 1 plus theta 2, okay, not just theta 2, because theta 2 is just from the direction of link 1 to link 2, that is theta 2, but here we are taking from the x-axis of the base frame or the inertial frame, right? So similarly in y direction we have P4 P3 is L1 S1 and P5 P4 is L2 S12. So x is P2 P1 plus P3 P2, which is L1 C1 plus L2 C12. Y is P5 5p4 plus p4 p3, which is L1 S1 plus L2 S12. Alright, so the correct answer is L1 C1 plus L2 C12 and L1 S1 plus L2 S12. Okay. Now the next question is, what's the inverse kinematics is defined as given the position and orientation of the end effector of the last frame, find the, and we know that it's position and orientation of the remaining frames. That's how we will get the joint angles also. The texturous workspace is the region in the work volume where the end effector, so texturous workspace is where the end effector can reach in all orientations, right? So reachable workspace is at least one orientation, and texturous is in all orientations. For the 2 degree of freedom planar manipulator shown in Q4, given xy, how many solutions θ1, θ2 are generally possible, not near the outer and inner boundary of the workspace? So this is the 2R manipulator case, and the point is not at the edge of the workspace, so it's a point inside, well inside the workspace. So how many ways to reach it? As I had shown, there are 2 ways to reach it, right? So the answer is 2. The function a tan 2 computes the tan inverse using only, so a tan 2, its range is minus pi to pi, so it uses plus sine and plus cos values, right? Now for the 2 degree of freedom 2R planar robot in Q4, we have the xy positions, right, and the link lengths. So find the value closest to θ2, right? So since we have derived the expression of θ2, right, that cos θ2 is px square plus py square minus L1 square L2 square and 2L1 L2, right? So θ2 in this case, so we have the numbers already, 1.83 whole square plus 0.75 the whole square minus 1 by 2L1 L2, that is 2 times 1 times 1. So this comes out to be, if you would calculate, this comes out to be 0.9557, and then if you take cos inverse from this, or not cos inverse, you should calculate sine θ2 by doing 1 minus 0.9557 square, and then you should do a tan 2 sine θ2 cos θ2, and again there will be 2 values of θ2, and since here you have all the distinct values, so θ2 you will get close to 17 degrees. Now, for the problem given in Q9, find the value closest to theta 1, right? So, one way to do is that you use the analytical expressions derived above, and you can basically evaluate the value of theta 1. Another approach can be a numerical approach. So, let me just introduce the numerical approach here, right? So, the expressions that we have is px is equal to L1 C1 plus L2 C12, and py is L1 S1 plus L2 S12, right? Now here, since we know cos theta 2, we can expand these expressions. So it can be written as L1 C1 plus L2 cos A plus B is cos A, cos B minus sin A sin B, and similarly this can be written as L2 S12 is sin A cos B plus cos A sin B, right? So we will put all the known values. The known values are C2 is 0.9557, L1 L2 are 1, Px is 1.83, and Py is 0.75, right? So the first equation for the x coordinate, we can write 1.83 is equal to C1, because L1 is 1 plus L2 is also 1, so 0.9557 C1, and sine theta 2, or let me, rather than putting values, let me write them as trigonometric expressions itself for better understanding. So C1, then L2 is 1, so it will be cos 17 degree into C1 minus sine 17 degree into S1, and the second will be 0.75 is equal to S1 plus cos 17 degree plus sine 17 degree C1, right? So if you put in the values of cos 17 and sine 17, what you will get is, I'm writing down now, you will get basically a system of, I would not say linear equations, but a set of equations in which cos theta 1 and sin theta 1 would be unknowns, and so it can be written like a matrix time a vector. So this is the known part. Unknown is C1 and S1, and this is equal to 1.83 and 0.75, right? So now this is a familiar form in which this is matrix A, this is unknown X, and this is the known vector B. So, and since A is a square matrix here, so if you can see determinant of a here is 1.956 the whole square plus 0.293 the whole square, right? Not equal to 0. So this means that a is invertible, right? So x will be a inverse b, right? So when you do this x a inverse b, you will get c1 s1 is equal to some numerical values here, right? And then you can find theta 1 is equal to a tan 2 s1 comma c1, right? So that's how you get theta 1, and in this case you will get it close to 14 degrees. So I finished the 10 questions in the previous year's week 3 assignment, and this will help you in solving the questions that you will be solving in the upcoming assignment. So apart from this, let me check my notes if I have some topics left for discussion. All right, so let me just summarize what we have studied in this session. So we first saw the need for knowing the kinematics, the inverse kinematics and the forward kinematics, ways of doing kinematics, especially inverse kinematics, the analytical and numerical. Then we took a deeper dive into IK. So analytical IK of 2R manipulator, right? And then we saw the number of solutions in IK and existence of solutions. And finally, previous year assignment we solved, right? So this was it from my side for today. In the upcoming lectures, we will study about Jacobians and some more depth into kinematics. And if you have any questions, we will discuss it in the next discussion hour, and you can also use the discussion forums on the website of the course. All right, so that's it for today, and we'll meet next week at the same time. Bye.